All right, so this is the second half to the lesson on section 5.2. And while the first, or the previous lesson, I should say, the focus of that was looking at an equation of a sinusoidal function and looking at the equation, developing a sense for how the graph appears. Essentially going from an equation to a graph. Well, this is the other way around, where essentially we're going from a graph to an equation. And let's get straight into it. So again, I start off with, in general, we're looking at sinusoidal functions, so functions that can be modeled with sine or cosine. Remember, again, this is mostly review. Amplitude is essentially just the same as the absolute value of a. The center line, actually the amplitude as well, can always be found by going max minus min divided by 2. The center line is always the same as your k value, your constant, your vertical translation, or I'll say it's at y equals k. However, it's also the same as the average between the high and the low values, the max and the min. It's the same as, or I could say it's the same as the mean between the max and the min, which is, in this case, going to be max plus min divided by 2. That'll always tell you where the center line is. And the period or wavelength, we've noticed, is always the same as 2 pi divided by that b value. However, if I take that equation, I can rearrange it. If I solve for b, if I imagine I multiply both sides by b and then divide by the period, I get this. I get the b value is always the same as 2 pi divided by the period, or the wavelength. So again, these two equations I have here are related to one another. Essentially, one is solved for period, one is solved for b. Okay, so the hardest part you're probably going to find about when you're trying to determine the equation is to determine the phase shift. Or that's, for a lot of students, that's one of the more difficult parts. And so I'll read this, but really, we need to use it. So first, you always have a choice. Any function can be modeled, any sinusoidal function can be modeled with a sine function or a cosine function. It can also always be modeled as a positive sine function or a negative sine function or a positive cosine function or a negative cosine function. All are possible. Usually one is kind of the easiest, but all are always possible. So you can start to get a sense of how this can be a bit confusing. But first, if you want to use a sine function, you have two choices to figure out the phase shift. First, you need to find a point on this where the center line, find a point on the center line where the function is increasing. If you can find a point on the center line where your wave is increasing, that x coordinate is going to be the same as minus h. Or you can find a point on the center line where the function is decreasing. So the function is going down at that point. If you do that, your phase shift will be, again, the same as minus the x coordinate, except you also got to make your a value negative. You got to imagine your whole graph being flipped around. All right, again, we'll use these things, but what if you want to use cosine? Well, cosine is actually, I'll say quite often cosine for applied problems is easier because you have to find a maximum, and quite often that's something you know in the question, the maximum. If you can find the maximum, wherever the x coordinate of the maximum is, that's your minus h value. That's what's going into your equation. Or you can find a minimum. But if you do that, you have to imagine your cosine wave being reflected vertically, which means you also have to make a negative. So many options. All right, so let's look at this one right here. Okay, I want to come up with two possible sinusoidal functions, one with sine, one with cosine. And I'll do the easier, what I think. In this case, one might be easier. That said, regardless if I'm using sine or cosine, the amplitude is going to be the same. And the amplitude of this and the k value of this, I can tell quite quickly by just looking at the graph. For example, I can see the center line is right here. And I can see the amplitude is 3. I can just see that. So I know my amplitude is 3. And my center line I can see is also at 3 in this case. Okay, so I know my a value. I know my k value, the center line. Okay, also, it doesn't matter if it's sine or cosine. The period is the same for for whichever model I use. And so what's the period of this function? Well, let's look. Let's go from here. I'll change my color. Let's go from here to here. Horizontally, what I'm showing in green, that is one full wave. That's one full cycle. What is that? How long is that line? That is pi units, especially if I hadn't scribbled over the x-axis so much. So I can see the period of this function. Not the b value, the period is pi. Okay, so therefore my b value is going to be 2 pi divided by pi, or 2. Okay, my period is pi, so my b value is 2. Which really, if you think backwards, is completely unsurprising, if that's even a word, because normally, whether you're dealing with sine or cosine, the period is 2 pi. Well, in this case, the period is pi. So I know there's been a horizontal compression by a scale factor of a half, and a horizontal, for any function, a horizontal compression by a scale factor of a half leads to where you have your input being multiplied by 2. All right, so with that said, now what's going to be easier for me in this case, sine or cosine? That's sometimes a subjective, but I'm going to start with cosine, because if I want to use a cosine function, I need to find a max or a min. And it's hard not to be automatically drawn to the tops and the bottoms of these waves. So, I could use either of these points for a max. I could use either of these points for a min. So already there's 5 possible cosine waves I could come up with. I'm going to go with just the first positive maximum, this point right here. Okay, so if I'm using cosine, I have to have, I'm going to have, if I look right here, this is at pi over 2. So I can imagine a positive cosine function translated pi over 2 to the right, which means my h value would be negative pi over 2. That's if I use a positive cosine function. However, another option is to find a minimum, and which in this case is going to be a bit easier, because if I find a minimum, which is right here, what's convenient about that point right there is if I look at that minimum, that already is on the y-axis. I don't have to have a phase shift, which means my equation can be as simple as possible. And so I can use that as my starting point of my wave, but except cosine doesn't start at a maximum. Cosine doesn't start at a minimum. Normally it starts at a maximum. So I can use that point for my starting point. And again, I'm referring to, essentially, I'm now looking at this example right here. I'm going to use that point in red as my starting point, but it's a minimum of the wave, not the maximum. So all I have to do is I can make h equal to 0. I can have no phase shift as long as I make a equal negative 3. So I'm imagining a cosine wave being reflected vertically, also being stretched by a scale factor of 3, also being translated 3 units up, also being horizontally compressed, but no phase shift, and that will lead to this wave. And so if I put this all together, since my h is 0, my equation would be y equals negative 3 times the cosine of 2x, all of that plus 3. So the a value, the k value, I could figure out right away. The b value was, I still think, simpler than understanding phase shift, although you do have to remember how period and the b value relate. The hardest part is probably the very last thing I spoke about. Okay, keep in mind again, I mentioned how I could have used this point here. If I did that, my a value would be positive, but I'd have some sort of phase shift in here. But it'd be no benefit to that, so I'm not going to do that. Like I said, there's an infinite number of possible correct answers, so I don't want to spend just endless time looking at other possibilities. But I do want to mention how I can also use this with sine. So if I want to use sine here, I need to find a point on the center line, either going up or going down. Going up is probably easier because then I don't have to reflect it. And so on the center line, how would I look? Right here. That point is on the center line, and it's going up. So I'm going to use that as my starting point. But unlike before, it's not on the y-axis, so I have to imagine a horizontal translation to the right. How many units? Well, pi over 4 to the right. So my h values, I'm not very good at making 4s apparently. Let's try that again, pi over 4. So I have to imagine a sine function being translated pi over 4 to the right in order for it to match up with that point there. There's other options, but I think that's the easiest. And so I'm not reflecting it vertically. And so my wave here would be y equals positive 3 times the sine of 2. Now I have a phase shift, x minus pi over 4, and all of that plus 3. Notice how similar my two equations are. In this case, my cosine function I think is simpler, but they both have the same amplitude, they both have the same b value, they both have the same vertical translation. The only difference is the sine function has to have some sort of horizontal translation. And that's because if there is no horizontal translation, a sine function starts at the center line. But this, if I look at my wave that I gave you, it starts at the bottom, at the minimum. Again, start being 0. All right, similar question, but this time I'm not drawing the entire wave. I give you just some key points, the maximum and the minimum here. However, what I would do right away is kind of sketch out this wave. What does this wave kind of look like? It must look something like this. And why not keep going? And let's figure out how far over my next maximum would be, which I have a graph, so I can see from here to here is half my wave, and that is 5 units. So count another 5. 1, 2, 3, 4, 5. I know my wave must make it to here. So I'll finish my graph like that. There we go. So I can see now the period of this function is 10. Not 10 pi, 10 units. So now I says determine an equation. I'm just going to come up with one equation. I want to come up with an equation that that is not needlessly complex. But first, regardless if I'm using sine or cosine, the amplitude is going to be the same. And I can see the center line right here. So I can see the amplitude is again 3. So A is 3. I can see the k value, the center line is at 2. I just drew it. Keep in mind, if I didn't have this drawn, I would have to look at the coordinates of my maximum and my minimum and find the difference between them to figure out the center line and the amplitude. But I have a graph, so I can just visualize it. My b value is always 2 pi divided by the period. Well, the period I said is 10. 2 pi divided by 10, I might as well simplify this down to pi over 5. So that's, again, my b value. So that's what's going into my equation. All right, so I know my amplitude, I got my a value, got my k value. Again, all these things I have here relate back to the same transformations we've been using in this course since the very beginning. So all that's left now is decide, do I want sine or cosine? Well, in this case, cosine I think is definitely easier, because if I want to come up with a cosine wave, I need to find a max or a min. That's what I literally gave you. That's all I gave you in the beginning of the question, just a max and a min. If I want to use sine, I have to find where my graph crosses the center line, which is approximately right here and here. But I'm not a computer. I didn't put a ton of effort into drawing this super well, so I don't really know exactly where those center line points are. I could figure them out. It's halfway between the max and the min, but why bother doing any of that work when I can just use cosine? So I'm definitely going to use cosine here. So all that's left now is to figure out what's my h value going to be. Well, for cosine, I need to pick a max or a min. Why not just go with this maximum right here? Okay, and if I look at this value right here, this is at -2. So I have to imagine a maximum on a cosine being translated 2 units to the left. I don't care what your function is. If you want to translate it 2 units to the left, you want to add 2 to your input. So my h value is +2. And so put this all together. My equation will be y equals 3 times the cosine of pi over 5 times, brackets are key here, x plus 2, all plus 2. Notice there's many reasons that you can find this challenging. But it all does come back to translations at the beginning of the course. But I think one of the reasons that people find this challenging is, first of all, they don't have sine and cosine, the basic sine and cosine waves internalized yet. So when I talk about how a sine function starts at the center line and goes up, that's not so, there's the bell, not so obvious to them. Other reasons are there's just so many possibilities. I could have used a negative cosine function. I could use a positive cosine function, but using this maximum right there. I could use a negative cosine function at that minimum. I could have figured out where these center line points are and use sine. There's so many options. Because these waves just repeat. They're periodic, they say. So there's always going to be an infinite number of correct possible answers and an infinite number of incorrect possible answers. That leads me to the last problem, which is kind of the reverse of last day's final problem. So last day, I gave you an equation of a Ferris wheel in London. You want to use it to kind of figure out the basics of the graph. This is kind of the other way around. I want you to come up eventually with an equation, and then we'll use it quickly. So here's another Ferris wheel. This one's in Las Vegas. I give you some information about the Ferris wheel. The Ferris wheel is 550 feet in height with a diameter of 520 feet. So the distance from here to here is 520 feet. Oh, that's a bit too small to read. Okay, but the total height from here to the ground is 550 feet. Okay, which means I can tell my, not surprisingly, it's suspended above the ground because the actual Ferris wheel is 520 feet in diameter. Passengers get on at the bottom, not surprisingly, and it takes 30 minutes to go around. Find an equation that relates height to time. Okay, so first, what I would highly recommend doing is making a sketch of how this information must relate to a wave. So let's create an X and Y axis or an H and T axis. So I have height and time. What do I know here? I know you get on at the bottom, and it takes 30 minutes to go all the way around. So I'll put 30 over here, and I know at that point that's one full cycle. I know the wave reaches a peak somewhere halfway at 15 minutes, I can see. And so I know the shape of how the height changes over time must look something like this. What else do I know? I know the highest point this graph gets to is 550. The lowest point, therefore, must be 30. It doesn't directly say that in the question, but it indirectly says that. The total height is 550 feet, but the diameter of the wheel is 520 feet, which means the bottom must be 30 feet above the ground. And I can now find the center line by figuring out what's halfway between 550 and 30. Well, again, if you want to find what's halfway between two numbers, you can just find the average between them. So in this case, it's 550 plus 30, max plus min, divided by 2. You get 290. And so with that said, I got my basics of my wave, and the reason that's helpful is I now have a visual to kind of build upon. So let's figure out my A value. My A value, in this case, this formula of max minus min divided by 2, for probably the first time in these notes becomes useful. You get 260. That's my A value. That's the distance from here to here, or from here to here. It's also the same as the radius of the wheel. My K value is my center line. I already found it. It's 290, but I found it by going max minus min divided by 2. So there's my center line. Okay, my B value, which relates to the period, is 2 pi divided by the period. What's the period of this wave? Well, that's the distance from here to here, which is 30 minutes. So it's 2 pi over 30, which reduces to pi over 15. All right, so now, do I want to use sine or do I want to use cosine? Well, if I want to use sine, I have to find out where my wave crosses the center line in one of these 2 points. I don't know immediately where that is. I could figure it out. For example, this point here is halfway between 0 and 15. But why do that when I can use cosine? And cosine, I need to find a max or a min. I can use either of those. I want to use this one right here. Because if I use that minimum right there, then I don't even have to have a phase shift, because it's directly on when x is 0 or when time is 0. It's not being, if I imagine a cosine wave being flipped vertically, it would start right there if I have no phase shift. So while I have lots of choices, the best choice for this is to use cosine, but make A negative. So make A not positive 260, make A equal negative 260. And that will give me the simplest possible equation, which I want to use in a moment, so it's good to have the simplest possible equation. And no phase shift. I'll say, so also H equals 0, so I don't need a phase shift. So my equation would be H, or Y, equals negative 260 times the cosine of my B value, pi over 15, times time, I don't need anything else going on there, plus my center line, 290. All right, so the last question, I've now finished the main part of the question. The last thing I ask is to try to use this to determine how long does it take a passenger to reach a height of 498 feet. So first of all, let's be clear what I'm asking here. This is the height, which means if I look back at my graph, 498 feet must be roughly, I don't know, about here. So, and the question says, how long does it take to reach the height? Well, it's going to happen 2 times, but I'm going to focus on the way up. So I'm trying to figure out what is that time right there. Although they're going to reach 498 feet on the way down, but I'm going to just go with on the way up. It's kind of what you imagine. How long does it take to get up to 498 feet? So how do I do that? Well, I have two options. I could graph this in Desmos and just look and see where h equals 498. Or algebraically, I can replace h with 498. So 498 equals negative 260 times the cosine of pi over 15 times t plus 290. Now, whenever we're solving a question like this, sometimes it can get quite messy. So we don't want to lose sight of the importance of solving this with graphing. What's important is to understand the idea of what it means to solve by graphing. Literally, graph the equation in Desmos and look at the height where it's 498, which I'll do afterwards. All right, but first, let's solve this algebraically. So it's going to get a little bit messy at one point, but let's start by subtracting 290 from both sides. And then also dividing both sides by negative 260. Okay, so I'm going to subtract 290 from both sides and then divide both sides by negative 260. If I do that, on the right-hand side, I have just the cosine of pi over 15 times t. On the left-hand side, I get negative 0.8. Sorry, Mr.
Are you behaving yourself, sir?
I am, Mr. Husick. I'm actually recording something right now.
Oh.
Yeah, no, it's okay. You've made a guest appearance on this recording. So I'll be done in like 5 minutes, though. Are you in for next door?
I'm in for Susanna for the morning, and I'm Lee Bouquet in the afternoon.
Oh, okay.
And I'm Lee on Tuesday and Wednesday, too.
All right, do you want to say hello to my pre-calculus 12 class?
I don't want to say
All right, see you, bud. And so I want to solve this. So how do I solve this now? Well, the key idea now is first realizing I'm trying to figure out where cosine is negative. Okay, and where cosine is negative 0.8, which is not a special angle. If I was asked, if it ended up where cosine equals a half, well, we should have memorized that cosine, we should know where cosine is a half. But we don't know where cosine is 0.8, or negative 0.8. And so how can I approach this? We have lots of options, but one option is, like up here, to get rid of the plus 290, I subtracted 290 from both sides. To get rid of times negative 260, I divided both sides by negative 260. So in essence, I want to cancel out the cosine function, and I want to apply that to both sides. So how do you cancel out a cosine function? You apply the inverse cosine function. And so I want to find the inverse cos of both sides. I'll write it like this. All right, so I'm going to find the inverse cos of this side and the inverse cos of this side. So inverse functions cancel each other out, so all I have left is pi over 15t on the right-hand side and the inverse cos of negative 0.8 on the on the left-hand side. And so if I go to my calculator and I type in the inverse cos of negative 0.8, it gives me 2.5 equals pi over 15t. Notice it only gave me one value. There's an infinite number of places where cosine equals negative 0.8. Your calculator will always just give you one. But in this case, it's a fairly, it's the first positive one, but you always got to be careful. And again, there's so much complexity here. Essentially that if I was just to ask you, where does cosine equal negative 0.8? There's an infinite number of places. But I only want one of them. And so the calculator will always just give you one, which is why, again, graphing is extremely important here. That's it. I've gone through the hardest part, so now I just need to multiply both sides, or divide both sides by pi over 15, which dividing by pi over 15 same as multiplying by 15 over pi. And so I get about 12 on one side and t on the other, so it takes about 12 minutes to reach that height of 498 feet. That's solving it algebraically, which in this case was doable, but chances are there were some parts you found quite challenging. So let me just finish off by comparing this to solving this graphically, which is so important. Okay, I'm going to switch to Desmos here. And I'll first type in my equation with y equals negative 260. Helps if I type it in properly. Negative 260 times the cosine. Pi over 15 times x, all that plus 290. Okay, before I do more, let me adjust my scales. Let me compress my y scale down. Let me compress my x scale to kind of see one full wave nicely. There we go. There's one full wave. Notice I start at 0. It takes 30 minutes to go around. There's my peak. Okay, so how can I use this to figure out how long it takes to reach a height of 498 feet? Just write another equation where y equals 498. And then there we go. There's my answer. Notice how superior that was in terms of efficiency compared to what I did before. I can also easily find the other answer. After 18 minutes, I'm at 498 feet going down. That was honestly superior in terms of compared to solving it algebraically in this case. And while you won't be able to use a phone on a test or something, this idea is crucial. So please understand this. Personally, I way prefer this than what I did before. And the answer I had before was no more accurate. It's not like that gave me a better answer than this. Okay, we need to understand both, but in this case, as equations get a bit more complex, solving something graphically is so important, and a lot of students really undervalue it. And so in this case, wow, that was a lot nicer, I think, than all of this, but led to the same answer. All right, so I'm going to stop here, see if Mr. Hughes